All right, let's talk about carboxylic acids. Carboxylic acids contain a carboxyl group at the end of a carbon chain. It's a C double bonded to an O, bonded to an OH. If it's ever typed out or written out somewhere, you might see it as a COOH. You need to know that that's what it's talking about. It's not talking about a C bonded to a C to an O, bonded to an O, bonded to an H. That is not true. Okay? Naming, we use the ending anoic acid, and the carboxyl carbon gets number 1. So here I have a longest chain of 2 carbons. So I'm going to use F, and then I put on the ending anoic acid. This is also known as vinegar. Although the vinegar we use is watered down tremendously because, or else it would be quite a biting taste. This guy, it's 4 carbons. I've got, I didn't actually draw on some H's here. It's number 1, 2, 3. So off of number 3, I've got a fluoro group. And then I guess I just go straight into the root, butanoic acid. The COOH group is very polar. Yes. Why? Because there's my C double bond O bonded to an O bonded to an H. I've got this is negative, this is positive, this is negative, this is positive. There's lots of charged areas around here. So your melting point, your boiling points are going to be high. Solubility in water will be high, but only if the number of carbons is small. How polar are they? Often one molecule's carboxyl group will line up with another one's, and I will get this thing's negative and this is positive, so I will get attraction here and here, and often they will stick together. That's how polar they are. And these molecules are called, these double molecules are called dimers. When they're so polar they stick together, they're called dimers, and carboxylic acids are often dimers. Acidity. Why does a C double bond O bond OH give off this, and not the whole thing? Because often when we have molecules that have an OH in them, we immediately think that's a base, but this is actually an acid. I'm not even sure oh, I know what I want to put here. Why does it? Because of our old friend resonance. It's not about what leaves the molecule, the H or the OH, it's what's left behind is the key thing here. So here is a carboxylic acid, a general one, okay? And I reacted with water because H plus ions, because this is an acid, this is coming off. They never just hang out by themselves if they're in water. They always join up with a water molecule to form H3O+. So this and this come together to make that, and I'm left with this thing. Okay? What do I have? I have R attached to a C, attached to an O. Now it's an H plus that came off, so this O has got a negative charge on it, and then I still have the double bond O. Okay? So the question is why is there going to be a single bond here and a double bond here? Could it not be the other way around? if we went through the whole process of looking at hybridization, this would have a p orbital sticking up and down, this would have a p orbital sticking up and down, this is going to have a p orbital sticking up and down. There's going to be a couple electrons here, electron here. I'm going to have the possibility of them all sharing this negative charge. So the other possibility, whoops, right? The other possibility is this. Yes. And because I can share this negative charge between two O's, that means what's left over, this thing, is more stable than if I had ripped off the whole OH. So again, because it can share this negative charge, and this negative charge is not wanted, once it's being repelled by other electrons that are hanging out here, but because I can share it between all of these, it makes it, what's left over, more stable than if I just ripped off the whole OH. So one might say here, if I'm looking at this ion here, that I've got an O and an O, yes, and I've got, it's not a single and then a double and then a single, flipping back and forth. It's kind of a combination of both. So you might say that it's like having 1.5 bonds here between each C and O, and because I can share the negative charge, it's like this has a charge of -0.5, and this has a charge of -0.5, and that just makes this structure, what's left behind, more stable, because it is all about what is left behind. And that is a brief look at carboxylic acid.